To illustrate the idea of comparing several means, we'll look at this example of an experiment in which a server wrote messages on the bills, randomly selected messages, to customers, and then recorded the tip percentage left from each customer. We have 3 different messages here that were left on the bills: a good weather message, a bad weather message, and no message. So rather 3 different message groups. So our no message is the control group. The good weather message is where the server says the weather is supposed to be really good tomorrow, so delivering good news. And the bad weather message is a case where the server is delivering bad news. So we're curious to see whether this message has any impact on tip percent. Because we have 3 different groups, we can't do this by a simple mu1 minus mu2 kind of analysis, right? And if we try to generalize this to more than 2 groups, we find that it's fairly difficult to come up with an expression that we think would really accurately capture all of the different ways that you could have a difference in these groups. So this is why we need a multiple comparison type test to look at this. We need something that's going to look at 3 groups and take a mean over each of those 3 groups and detect any difference at all in one of those 3 groups. So here we have a box plot that shows us what the data set itself looks like, and from this box plot it does appear that our good weather message may have had some positive impact on tips on average. It also appears that this bad weather message may have had some negative impact on tips if we control that to no message at all. However, we do see that the difference for the positive message, the good message, does seem to be a bigger difference overall than the difference between none and bad. So let's go ahead and address the question of whether a message about good or bad weather has any effect on the tip percent that customers leave. First of all, from the samples we have observed that it does appear that good weather messages increase the tip percent, and that bad weather messages may have some negative effect, may actually decrease the tip percent, although that's not as big a difference. So we can put this into words in some way. The good weather message appears to bring in higher tips. The bad weather message may hurt tips a little bit too. For our hypotheses, we can see that the null hypothesis is that all 3 means are equal. And then, similar to what we've seen with other multiple comparison type of tests, the alternative hypothesis is not that all of them are not equal, but that at least one pair is not equal. So the mu I and mu j, that's just filling in any 2 subscripts out of the 1, 2, and 3. This is our way of saying that at least one pair of means is different. To get into the topic of analysis of variance, which we refer to by this acronym ANOVA, it's helpful to first look at these 2 examples here of comparisons of 3 groups. So this is one quantitative variable measured over 3 different groups. We're going to assume that the mean, or the mean, which is also the median because these are symmetric, of the first sample is the same in both A and B, and that the median of the second sample is the same in both A and B, and the same is true for the third sample. So we can see by drawing these lines straight across that the centers of these distributions line up. The question that we're interested in addressing with these is which of these 2 pictures, A or B, gives us stronger evidence that the means are different from one another. And to answer that, it's now helpful to draw a line from this median over to the next distribution over. So looking at the next group in our study. It looks like in this case my median is still in the middle half of this next distribution. If we compare that to what happens over here in B, when I draw a line over from the median, I am very close to an extreme value in the next distribution over. So the median is very close to the maximum value. In the next group over. And if we were to extend that line a bit further, we would see that it completely misses this other distribution. Coming back to our first example, if we were to extend that line over a bit, we would at least still be in the third distribution. So in this second picture in B, we would say that we think these means are different from one another. So we would say here we have in B stronger evidence of a difference in means. Whereas if we look at this first picture, because the median was still in the middle half of the next distribution over, this is slightly weaker evidence of that same difference. We don't really know statistical significance from this picture. For one thing, we don't know how big the sample is from these box plots. It's possible that sample is only 5 for each illustration, in which case maybe that's not enough, whereas if this sample is 10,000, then that almost certainly is enough evidence to get us some pretty strong statistical significance. So we're not getting statistical significance from these, we're just getting a general idea of the strength of the evidence in these two pictures, where if we assume the same sample means, having less variability, having the distributions a little bit tighter around that mean, gives us more statistical significance for a difference in means. So this is one way of putting into words what we want to take away from this picture, that for the same sample means, having less variability in each group gives more evidence of a difference in means. In other words, that difference between two means is all relative to the spread of the distribution. We can't really say how far apart are 80 and 90 until we know what typical values are around that 80 and what typical values are around that 90. For this reason, the test statistic that we use for comparing multiple means has this form. It's a ratio where the numerator is the variability between groups. That means how far apart the sample means are from one another. It makes sense that as this value gets larger, we have more evidence that the means are different. And the denominator is the variability within groups. That's the average. I'm going to put the word average in quotes here because there is a specific formula for calculating this, and it involves a bunch of sums of squares, which we won't really get into, but we can think of this as being an average variability in each sample. So we can also see from the picture that we just looked at that as that variability within each sample gets smaller, which means we're looking at a picture more like this second one, we would want the statistical significance to increase, right? We would want to get to say it increases. It's a little bit hard to interpret, but we would want to feel that we get stronger statistical significance. Well, as that variability gets smaller, because we're in the denominator, we'd be dividing by a smaller number, and therefore the F statistic, the whole thing, would get bigger.